All right, so we've got a wealth of questions about the discussion board and the kinetic versus thermodynamic products. And I think a lot of the question I'm getting here is actually kind of trying to, I hate to say misapply a theory, but trying to think about the theory way more than it's actually there. So the discussion board this week, or for last week for Organic 2, was focusing on basically iterations of this compound. So one, two. And we got terminal, middle, undying. And it asked you what were the products, and the hint for how many products there were was kind of based on the points. So 2-methyl heptane is worth 1 point, 6-methyl 1-heptene is worth 1 point, 6-methyl 3-heptene is worth 2 points. So there's 2 products there. And the 6-methyl 1,3-heptadiene is worth 1 point. Now, the thing to keep in mind here is that Lewis theory really doesn't quite predict resonance. Like, you can draw resonance from a Lewis theory standpoint is multiple solutions to the same Lewis structure. And resonance does occur in the sense that macroscopically we see a mixture and we do see interconversion. But the thing to keep in mind here is that when we have this resonance stabilization, that doesn't necessarily mean that this double bond is kicking around. And the thing is, like, there is an activation barrier to it. So it sounds like a contradiction, but it's more just an incompleteness of the theory. So if we look at, for all of these, we looked at the halogenation with Cl2 and light. And Cl2 and light, make sure it's all still kind of in camera there. Yep. Cl2 and light is going to do free radical halogenation. We're going to do a half equivalent to ensure that we only use 1 chlorine. And from Orgo 1, you should remember that tertiary is replaced before secondaries and primaries. This changes when we have the option of allylic carbons, and these are carbons that are adjacent to a double bond. So our allylic carbon is going to be here, 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 here. So this is where we're going to get the primary amount of substitution. Now, the reason why we're going to get the substitution is that our first step here is to form a radical. And this radical is stabilized by resonance. But the thing is that we don't see a lot of this flipping around. It is stabilized from a more complicated standpoint that because this is sitting in a p orbital, it now can associate with the double bonds. So you really have to look at this more from a molecular orbital theory standpoint than from a Lewis theory standpoint. We're going to draw a resonance structure showing this popping back and forth, but that's really not what's going on with these molecules. What's going on is that because this is now in a p orbital, it can associate with this double bond, and that unloads some of the burden. But we're still going to get mostly substitution at the adjacent carbons, and we're not going to see these double bonds flipping around. So for all of these, we're going to get substitution at the allylic carbons, and we're going to get 1 substitution. Now with this one, we have 2 possibilities. They are both secondary, and so you're going to get one where you get substitution here, and one where you get substitution here. So that's where your 1 point, 1 point, 2 points, and 1 points come from, is that you need to get substitution here or here, and you would name them appropriately. Now, it asks you, how would you convert to 3-chloro 2-methyl heptane? And so that is this structure here. Now, if you look at all the products, this is the only one that uniquely gives you that 3-chloro product. These are equally likely, so you're going to see both this product, oops, double oops, and this product. So you're going to see both the 3-chloro and the 2-chloro here being formed. So this one, with the diene, this is far more likely to actually give you the product you want. And so when we hydrogenate this product, we end up with the desired alkene. How do we know when to draw these resonance structures? So it'll come up in the notes when you need to start drawing it. So a big example of when you need to draw the resonance structures are when you're dealing with, where's my eraser? When you're dealing with keto-enol tautomerization. So one we'll be talking about for test 3. This is not technically resonance. This is tautomerization, which is a special case of resonance. So this is when we would concern ourselves with drawing the resonance structures, because these are actually both isolatable and you're able to actually prove they exist. But something like this, we're going to act like resonance is what's going on. To move this pi bond is not as simple as it sounds. You're having to break this bond and form a bond here. So there's a bond breaking activation. Here we're just moving a hydrogen back and forth. It's a lot easier. And because we're moving a hydrogen back and forth versus like having to move a whole bond, breaking a carbon-carbon bond, we find this actually is absurd. This, from what I understand, is a lot less absurd because, again, you're trying to apply Lewis theory, which doesn't really look at atomic orbitals, to a situation where atomic orbitals matter. And even in the case of this is actually a reaction catalyzed either by acids or bases. So this is a reaction that's going on. Again, Lewis theory is going to oversimplify this and say that the bond is moving when in reality you're having to break a carbon-carbon bond and reform other bonds. So we don't really need to worry about this much right now with doing analytical problems. Yeah, more or less, the big picture is the more important part. And so again, I think what you're seeing here is that the theory does not adequately explain what's going on. I know there are people that are going to argue with me about this, but Lewis theory is an incomplete theory. Again, it predates atomic orbitals. Molecular orbital theory is going to explain this a lot better by saying that basically if we put the molecule on its side, there is some association between these two. So there is some molecular orbital formed by the interaction of this free radical orbital and the double bond. But this is not to imply, molecular orbital theory would not imply that this bond is breaking and going back and forth. It would say that you've actually created two different orbitals. So you've got one orbital due to the pi bond, and you've got one orbital due to the radical. And when they interact, you inherently create more stability for the two electrons. So you lower the energy of the two electrons while increasing the instability of the radical, but this overall increases the stability of the molecule. So this is how I understand it from a molecular orbital theory standpoint, is that you're not really flipping the bond back and forth so much as that these two form their own molecular orbitals. And even though it increases the energy of this molecular orbital, it does overall stabilize the molecule, which is what creates a more stable radical. But again, if you're looking for a Lewis theory explanation as to why, the Lewis theory explanation is going to say that the bond is bouncing back and forth, and I think that's way oversimplifying what's actually going on. It's how it's explained, but if you look at any textbook and you ask them, common example I saw was this plus NBS, which is a free radical reaction. They always put the radicals here. Never have I ever seen them put a bromine here with this. And I think that's implying from a lot of the textbooks that this idea that this bond is bouncing back and forth really isn't a real idea. All right, thermodynamic versus kinetic products. So I think I say this in the notes. I really, really hate this terminology. Yeah, you would use to, although honestly you would just run it in excess. You would just say PTH2, excess H2, just to ensure that you got complete catalytic hydrogenation. Particularly with free radical reactions and halogenation reactions, we do need to specify how much we're running, because typically with those we're not trying to run them to completion. So in reality, even if you had this molecule and you just had Cl2 in light, first you would get halogenation here, and here, and here, and here, and here, and here, and it would just keep going and going. So we have to specify this half equivalence to say that we are going to terminate it as best we can on the first halogenation. Typically with hydrogenation, we're not trying to terminate the reaction, so we're just going to say H2PT with the excess being implied. If after resonance it is more stable, is the majority of your product? So I'm not quite understanding your question. My guess is you're asking, like, do we ever concern ourselves with what would be the resonance product? The answer is no. For these types, for allylic hydrogen substitutions, we don't worry ourselves with what would be basically the resonance product, because again, I don't think particularly in this case resonance is being used to explain what's going on, but resonance products are rarely ever seen. So for me, again, this is explained better with molecular orbital theories to say that by creating this vacant p orbital, half-filled p orbital, you are creating the opportunities for stabilization through interactions, through pi interactions. But again, I've never seen a textbook claim that this resonance occurred and they got substitution all over the molecule. The only substitution they get is at the allylic hydrogens, and that's it, which is implying that this bond is not moving around. All right, thermodynamic versus kinetic products. So I think the confusion here is more in how the mechanism plays out. So again, the mechanisms we use in organic chemistry are kind of approximations. Again, we're working with an incomplete theory here, so we're definitely going to find gaps where gaps in the theory where things aren't quite well explained. You're welcome. So, first of all, my 2 cents. I hate these terms kinetic and thermodynamic. So kinetic is the fast product, and then thermodynamic is the one that occurs at high temperature. This is misleading because the thermodynamic product should actually be defined as whatever is the most stable product. This isn't necessarily true. Your thermodynamic product may actually be the less likely or less stable product, but all this is saying with thermodynamic product is that this is what's achieved at high temperatures. So the question is, how do you view this reaction? So traditionally when we drew alkene reactions, we had H plus Br, and we get attack of the H, and this ends up generating a carbocation, and then we have our Br, which undergoes nucleophilic attack. Another way to consider this reaction is that momentarily we generate a carbocation and an anion, and then your anion attacks the bromine, this generates your H+, and then your bromine attacks. So the question is, how does that change your answer? So if we're going purely for negative attacks here, this would mean that the H is getting attacked, and we're going to generate a carbocation, and we can generate it one of two ways. We can either generate our carbocation on the tertiary carbon, or we can generate it by leaving it there on the allylic. And so this would imply an inversion. So this would imply here that you get an inversion of the, you basically would get an anti-Markovnikov product in the event that you had this tertiary carbon sitting beside as part of this conjugated system. So if this was the case, then we would say this would end up generating anti-Markovnikov products just by sheer merit of having them adjacent to each other. And your kinetic product would be this, and then your thermodynamic product would be the resonance where that moves around, and we get this. If you take it from the standpoint that the carbocation is created first, then your picture changes to say that the first thing we're going to do is create the most stable carbocation we can find, which is this. And then we're going to get our bromine to attack. And then by resonance, we will move our double bonds over. And then we will produce this product here. So how you view the mechanism will begin to change whether or not the Br gets added to the tertiary or the secondary by sheer merit of where does that carbocation appear. I think particularly with this problem, this is just a well-meaning problem that had unintended consequences. So the way I was taught when I did thermodynamic and kinetic products, and this was taught in reactor engineering, was that it is a Markovnikov reaction. But the difference between your kinetic and your thermodynamic is that the kinetic is going to be a Markovnikov reaction with a single bond between the adjacent bonds. Your kinetic product is going to have a double bond between them. So under that line of reasoning, if we have this molecule, your Markovnikov, if we were to choose which of these would be most likely to undergo addition, this is the one that's most likely to go addition, and so your Markovnikov would be this one, and your thermodynamic would be the Markovnikov with the double bond between them. So this is your kinetic, this is your thermodynamic. Now, again, it depends on how you interpret the mechanism. So we just kind of... So, explain it all again. So this is the way I was taught, that if you have any type of diene, conjugated diene, and you do kinetic versus thermodynamics, so K versus T. The reaction is Markovnikov regardless, so you would need to do something to get it away from adding the bromine to the most substituted carbon. The big difference between kinetic and thermodynamic is whether or not there is a double bond separating the bromine and the hydrogen that you added. So with kinetic, there is no double bond separating the bromine and the hydrogen you added. For the thermodynamic, there is a double bond between the bromine and the hydrogen you added. This does not consider the mechanism itself. What this does is just considers the overall process. But again, we can look at it from a mechanistic standpoint. So pathway 1 says we generate the carbocation first. Oh, kind of flipped. Pathway 2 says we consider the anion first. So if we form the carbocation first, that's by hydrogen attack. And if we do it by hydrogen or attack on a hydrogen, so what we're going to do is we're going to take our double bond and we're going to attack a hydrogen. And the most stable carbocation here is going to be one that is allylic to the double bond. And so if we are forming the carbocation first, this would actually form an anti-Markovnikov product, because we're no longer adding the bromine to the most substituted carbon. And there are arguments for and against this, because you could say, well, originally we had Markovnikov because we didn't have resonance stability. Now we have resonance stabilization, and so it makes sense that we would get an anti-Markovnikov. And so your kinetic product is where you add it there, and then your thermodynamic is where you get the resonance to get this. Now, if we go anion first, meaning that the double bond dissociates, the first thing we get if we generate our anion first, this is resonance stabilized by merit that we can move that. See if we can still see that. This is resonance stabilized because that anion can form a double bond between these two carbons and give us an anion further. So in this case, this would be Markovnikov, because we would get bromine attaching there to the most substituted carbon, and this would be inconsistent with what I was taught. Now, that said, this is not to say that what I was taught was actually correct. So based off what I understand of kinetic versus thermodynamic products, and again, a long time ago, kind of skimming from books to figure this out, even though this is how we would write out an addition to an alkene, it ends up generating an anti-Markovnikov product in the process. So that would imply that dienes are inherently anti-Markovnikov. Now, if we don't draw it the way we run the reactions of alkenes, but instead say that we end up generating a resonance stabilized carbocation, this would keep us getting a Markovnikov product, meaning the bromine goes to the most substituted carbon, and giving us this end result of the double bond between the two. So the question really is, do we get a Markovnikov or anti-Markovnikov product when we have dienes? And to be honest with you, I'm going to side with the Markovnikov pathway just because that's what I've taught. I think what you're seeing with the study packet was that was a well-meaning question, but it was not intended to open up this debate as to whether or not when you add HBr to these double bonds, does it act Markovnikov or anti-Markovnikov based on whether or not there's an adjacent double bond. So I know that's a lot to say, but there's implications depending on which mechanism you choose. If you choose a mechanism that forms a carbocation, you inherently have to put the carbocation adjacent to that double bond, which for the example you were looking at would make it an anti-Markovnikov reaction. I've never seen a book say that dienes can act in anti-Markovnikov fashion. They all behave in Markovnikov fashions. But that is the mechanism we write for alkenes. If we don't say that, if we say instead, well, really what it does is it does a bromine attack first. So bromine is going to attack the most substituted carbon because we're going to create a carbocation first, and that results in the anion being able to resonance. Then we still get a Markovnikov product. Everything behaves like we expect it to be. So to be honest with you, I don't know. I would need to go look this up. I've never been asked this question before, and I think it's purely by merit of the fact that when I wrote this question, it never really... Yes, so the implication here is if we go by the alkene mechanism for this particular example, we end up getting an anti-Markovnikov product. So if we just ignore the second double bond, we would put the bromine here on the least substituted carbon, which would be anti-Markovnikov. And I've never seen a single book claim that dienes have this ability to flip a mechanism from Markovnikov to anti-Markovnikov. I think really what happened here was that this was a well-meaning question that opened up a lot of questions it was not intended to answer. So I do not know which of these two mechanisms is correct, to be honest with you. My guess is that most books, when they present these kinetic versus thermodynamic products, inherently stick to very simple examples to keep from answering these types of questions. There is probably a very rich literature review out there to explain how this reaction actually works. But again, I don't know the answer to your question because I can see arguments both ways. Again, I know I know what I was taught, but that does not mean they taught it to me correctly. They may have been wrong and they were trying to force a Markovnikov product on the answer, because that made sense. HBr should be adding in a Markovnikov fashion. But maybe they were just wrong and they taught me wrong, and so I perpetuated this thinking it was correct. I was going off what the book told me, but again, the book doesn't give examples where you could conceivably get an anti-Markovnikov product just because of resonance stabilization. So I guess the best way to answer your question is we accidentally got a graduate level question in an undergraduate course. And I would just skip that problem altogether, acknowledging that you're probably not going to be dealing with anything that particularly complicated at this level. It was meant to be a simple problem that once it really got worked on, ended up being a lot more complicated than it was supposed to be. So an example of this are like the Diels-Alder products, right? Like the Diels-Alder problems can suddenly get super complicated because you have to consider all the different iterations. Metathesis problems, unless you make them very simple problems, can end up being very complicated problems. I think the same thing happened here where this was kind of an unintended consequence. We had a reaction that was basically supposed to be pretty straightforward. You either finish with the addition beside each other or you finish with the addition with a double bond between them. And by introducing this tertiary carbon, we ended up creating an accidental situation where you have to choose. Do you stick to the alkene mechanism and get an anti-Markovnikov product, or do you contradict the alkene reaction and say, really, it's nucleophilic attack by the bromine and we're still going to get a Markovnikov product, we're just going to kind of contradict the mechanism. So yes, it took me a while to understand your question, and again, I think a lot of it is that this problem was not meant to be this complicated, it just ended up being this complicated. hopefully none of the rest of them are giving you those types of issues. They should all be pretty straightforward. But like I was really trying to, well, I was also writing tests this morning too, but was trying to understand the best way to answer your question. And I think this is kind of where we're at, is that this just happens to be a graduate level question that's sitting in an undergraduate course by accident. If it makes you feel any better, this thermodynamic versus kinetic product, it is a concept that is being introduced at this level, which is more meant to kind of come up at a more senior level. Simple problem is if you just get rid of this double bond. And by symmetry alone, this ends up becoming a very simple problem. So we know we can't form a carbocation here, so our only option is to form a carbocation over here, because we have attack of by a hydrogen on this molecule. We will terminate with a terminal carbocation, which doesn't work. So our other option is to put it over here. Now you have two options here, because there is not really a justification for the stability of one over the other. So in this case, if we have, we can either have the attack here, or we can have the attack here. But if we have the attack here, we don't end up with the resonance stability, and so your options here are Markov-Nikov addition. Well, actually there's no option here for Markov-Nikov because they're equally substituted, so you get addition here, or you get resonance stabilization, and you get a terminal one. But you're not likely, sorry. But what makes this one easier is that where you're adding the double bond isn't really impacted by a tertiary or secondary carbocation. In both cases, it's a symmetric alkene, and so there's not a preference for Markov-Nikov or anti-Markov-Nikov, because there is no such thing as the Markov-Nikov or anti-Markov-Nikov products. You're adding to a symmetric double bond. They're both equally substituted. And because of that, you really can't have a wrong answer. There's really only one way to add it. So yeah, where we add them right beside each other, that's your kinetic. That double bond is thermodynamic. Now again, this is why I hate the term thermodynamic for this, is that if you sat back and said, well, really, in order to get this, I would need to create a terminal carbocation, that's not likely. I entirely agree with you. This is probably still going to be a minority product. The majority product is going to be where you add the HBr right next to each other. But thermodynamic here does not imply stability. Thermodynamic implies that at high temperatures you can get this, because at higher temperatures you make more unstable compounds more likely to occur. And that's what's happening here, is that at high temperatures it will be warm enough that you can stabilize a tertiary carbocation. So this is the most likely product, because this is a resonance stabilized carbocation, and this still obeys our alkene mechanism, and our thermodynamic product is when we're just add it further down. But you're probably going to find, particularly in the textbook, they work with a lot of very simple linear non-branched alkenes for this very reason. There is none of this ambiguity about which carbocation ends up being most stable. Yes, so for the thermodynamic product, that's the one with resonance. This does occur, it is observed, but the reason you have to go to high temperatures is that in order to make this bond move, there is an activation barrier for it. So if we wrote it as E energy versus time, we would have did it again. Okay, so we got hydrogen. So we've got our starting carbocation here. We've got the transition state where the double bond moves, and then we've got the final result where we've got the terminal carbocation. we're probably looking at an energy barrier that looks like that. Sorry. And so the reason why we need that high temperature is to get over that activation barrier EA. And it's not so much resonance, it's not going back and forth so much as we need enough heat to get that bond to move. And once that bond moves, then we've got this product to work with. Again, resonance is not really predicted by Lewis theory, and in this case, the answer saying that the bond moves back and forth is a gross oversimplification. Most likely what's going on is that this vacant p orbital that contains the carbocation is forming a molecular orbital with that double bond. Because they're creating orbitals with each other, we end up stabilizing, in this case we'll end up stabilizing the 2 electrons in this pi bond using this unstable p orbital which doesn't have any electrons in it. So basically we don't get any penalty for the carbocation. So I'll draw up here a little bit bigger. So if I had explained this molecular orbital theory, I need to stop writing that. The reason why this is more stable than this is because that with these two adjacent, we have the energy of the p orbital with the carbocation in it. We've got our pi bond with 2 electrons in it. These two can now interact because they have the right symmetry. We'll end up stabilizing the pi bond, which has 2 electrons, and our carbocation here doesn't have any, so raising its energy has no effect on its stability. Can you go directly from a kinetic to a thermodynamic product with resonance? So once you make the product, you can't interconvert. So if you've got 2 products, I'll just draw the H in, then I add it. So these can't interconvert, so you can't say like they resonate. In order to resonate, you can't make or break bonds. Again, the big exception to this will be polymerization. We'll talk about that in a couple of units. So basically, what helps you go, well, how to say this? We've got our starting material, and we go through our first reaction intermediate. And this will be present, and then at higher temperatures, it will begin to resonate and do this. So it's more of a process of our pathways. Before it gets attacked by the bromine, at low temperatures, we pretty much only get this, and then the bromine adds. At higher temperatures, we have a second pathway, which becomes accessible, where we form this terminal carbocation, and then we add the bromine. So we can't resonate between the products. They're last steps in a reaction. But while the reaction is taking place, the resonance is interconverting intermediates, so it's changing what intermediates are present. And that interconversion is what gives us the thermodynamic versus the kinetic. But once you've made those products, they can't be interconverted back. So the way to look at it would be a reaction pathway. So we have our starting alkene. We'll have our first activation barrier go to our first intermediate. And our first intermediate is this carbocation. Then we'll have a second reaction, second EA, where we add the bromine. So at low temperatures, this has a low enough activation barrier that pretty much that's the only thing that happens. When we do the thermodynamic product, there's a second barrier that appears, and this second barrier is our resonance product. And then that will react with bromine to give you this. So this is more what's going on. Now on the now for the kinetic product, we don't supply enough heat to the system in order to get over the activation barrier for the thermodynamic product. So low temperatures, there is a barrier to going to this second intermediate. At high temperatures, we have enough energy that we're able to go from this first intermediate to this second intermediate, which then reacts to give us the thermodynamic product, THD product. How do you teach which one of the major product? Temperatures. So there isn't an answer, a universal answer to your question about which one is more stable. It depends. In this case that I have on the board, the thermodynamic product is less stable than the kinetic product because you would have to go through a terminal alkene. Now, if I threw another carbon on there, and so in both cases we end up with a secondary carbocation, you would probably see that you get more and more of the thermodynamic product the higher you go in temperatures, but there's no relative stability difference between the kinetic and the thermodynamic product. So this actually is a thing that happens a lot in reaction engineering, is that the thermodynamic product is what you want, but the kinetic product is the easiest one to make. And the thermodynamic product isn't necessarily the more stable product, and it also has the higher activation barrier to get to it. So again, it's going to kind of depend on the reaction. I would say the way I originally had it drawn, basically we would consider at high temperatures the thermodynamic product to be the undesirable side product, or the one that's always minority. We're just increasing the amount of side product we're forming. In this case, maybe you're trying to get this you're trying to get this alkene inside. Actually, I'm looking at it now. I'm wondering if they're all not even just the same compound. But yeah, there's no universal answer because sometimes the thermodynamic product is more stable, and that's why a thermodynamic product is such a bad name for this, is that thermodynamically it may not be the most stable compound. It may not go through the most stable intermediates. The only thing thermodynamic means is that it has the higher activation barrier to get to the products. And you would have to look at the reaction and decide. Like, sometimes kinetically aren't the most stable. So we call these metastable states. So in a metastable state, you end up at a local minimum. Basically, your product that you make is the most stable product based on the energy you can get to, but there may be a more stable product that if you just had higher temperatures, you could rearrange the molecule and get to. And this is more of a discussion for like a senior level reactions engineering course. So if you have multiple bonds and you end up with many thermodynamic products, you choose the one that forms stable carbocations. You form the ones that require the least bonds to move. So each bond that moves is another activation barrier. So let's say we had the option of moving 3 bonds. One, two, three. And our first 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. So when we react this, we'll get our first product here, our second one here, and our third one here. And all these start from this starting initial kinetic product. So let's start with that one first. And we'll plot this as E versus reaction coordinate. So we start with 1, 2, 3, 4, 5, 6, 7, 8. Put our carbocation here and it's resonance stabilized. And your kinetic product would be, let's say we're adding bromine to it, is when you add the bromine here and you end up with the bromine on the second carbon. And again, we're just going to treat this as a hypothetical molecule that even though they may not look different, we're going to pretend that these 3 carbocations are different. To get to the second product, we have an activation barrier to get us to 1, 2, 3, 4, 5, 6, this product, and then it will have an activation barrier where it adds to the bromine. And then to get to the final one, we have another activation barrier. Where now we've moved that carbocation to the end, and then we add the bromine. So assuming that all three of these are equally stable products, I don't know that, basically, but assuming we had this hypothetical molecule where they were all equally stable products in the end, at low temperatures, this is the majority product. As we start increasing the temperature, we start giving enough activation barrier to get to the second product. At higher temperatures, we start adding enough activation barriers to get to the third product. And even in this hypothetical example where all three are the same, we're still going to form a majority of the kinetic product with less of this and even less of this by sheer merit of the fact that each one has to go over an activation barrier. Even if I set those activation barriers between the second and the third to all be the same, you still have to cross over it. And because you still have to cross over it, this is where that kinetic effect begins to play into effect, is that it takes time for this to jump over this product, over this EA barrier, and so this starts building up while you're waiting for more of these to jump over and form the third product. So you have your kinetic product, which is just the straight aggression across the double bond, and then you would have your first thermodynamic product, which was the moving one bond. Then you'd have your second thermodynamic product, which is moving a second bond, third, fourth, and so forth. And you would see them in their relative amounts. So first you would have a lot of the kinetic product at low temperatures. As you increase temperature, you start seeing more of the second product, then more of the third product, then more of the fourth product, and so forth. But you're still going to have a majority of the kinetic product. But it's not an issue of carbocation stability. That will kind of dictate how hard it is to go up to the next thermodynamic product. Well, so the thermodynamic product is implying that there is an activation barrier to go from one to another. So let's say this really did end up being a tertiary carbocation. I agree with you, that is the more stable one, and you would like to form that. But the problem is you still have an activation barrier to get over it. And so the term here is metastable. This is a metastable state. So your kinetic product, even if it's got a less stable carbocation than your thermodynamic product, you still have an energy barrier to get over. There is still an EA. And so a way to look at this is, if you look at the reaction of nitrogen and oxygen, this is favorable at room temperature. So thermodynamically, NO2 is more stable than nitrogen and oxygen. But the nitrogen and oxygen that you're breathing aren't spontaneously burning. You can't, to split nitrogen, it takes lightning strikes. It takes a lot of energy to split that nitrogen triple bond. So even though the reaction of nitrogen and oxygen would more favorably form NO2, nitrogen dioxide, at room temperature, a majority of the air you breathe is nitrogen and oxygen by sheer merit of the fact that there isn't enough energy at room temperature to make that reaction occur. The same thing is going to be true with your more stable thermodynamic product. I agree with you that it is more stable, and assuming that there was no activation barrier, that there was no penalty to go from one to the other, yes, you should form the more stable carbocation. But the problem is that you have an activation barrier. There is a hindrance to getting over you have to convert from your less stable carbocation to your more stable carbocation, usually in the form of bond flipping. That takes energy, and if you don't have that energy, it doesn't matter if it's more stable on the other side of the activation barrier. If you don't have the energy to get over it, you're stuck in your state, and that makes it a metastable state. And what the metastable here refers to is that it is stable by sheer merit of the fact that you don't have the energy to go anywhere else. Again, nitrogen and oxygen. NO2 would be a lot more stable than nitrogen and oxygen, but you don't have the type of energy at room temperature to break those nitrogen and oxygen bonds, so you're stuck with what you have. Now, on the other extreme, if you have a barrier and you start throwing more and more and more heat at it, in principle, you can tip the ratio between kinetic and thermodynamic products. So if the thermodynamic product really is the more stable product, if you supply more than enough energy to get over that barrier, then yes, you will produce a preponderance of the thermodynamic product. And thermodynamically, saying that correctly, you would have a thermodynamic distribution of products. But again, if you don't have enough energy to basically make it look like there's no activation barriers, you never end up with the thermodynamic product. Yeah, you would be given very simple questions like, okay, what's the kinetic product versus the thermodynamic product for very simple examples. And really, the only thing you're trying to do is kinetic versus thermodynamic. As far as figuring out like what's out there in the majority, that's not straightforward to do. This is why you take reactor design, is so you can figure out how to like get the products you want. But at this point, we're just trying to introduce this idea that you can definitely get rearrangements within a molecule. Sometimes you want that, sometimes you don't. If you don't want it, run it at low temperatures. If you do want it, run it at high temperatures. But also accept the fact that you're going to get a ton of the kinetic product unless you're willing to run at extreme conditions. Second to last problem on page 4 of the study packet, the one with the nitrogen, double nitrogen. Okay, let me download it. And let me download the solution sets to make sure it's not an issue with the solution set. Oh, that one's straightforward. Okay. So the one with the double nitrogens on it. Oh my, that's a big compound. Lots of 6-membered rings. Okay, so for simplicity, I'm not going to draw the rest of it. I guess I should. Okay, hold on. Double bond, double bond, double bond. And so you go through, ask you what part of the molecule is aromatic, and a big reason I did this was because students were like assuming whole molecules had to be aromatic, and that's just not true. Like parts of molecules can be aromatic, and the compound itself is still considered aromatic because it has that aromatic functionality. So this is exactly like a benzene ring. So what's happening here is that we have a ring, so we met our first condition. It's conjugated. We have 3 double bonds in a row, and we have 4n plus 2 electrons. So in this case, the nitrogens don't need to lose their lone pairs. There's actually an analogy for this. This is called pyridine. So pyridine is a nitrogen analog of benzene. This is also aromatic because we have the 3 conjugated bonds. So this meets all our conditions for determining aromaticity. We see conjugated bonds. There's 3 of them. We have the 4n plus 2, 2, 4, 6. And in this case, nitrogen doesn't need to use its lone pairs in order to add to the ring. It just uses its double bond. Page 5, the very last problem. Oh, man. Actually, I disagree with one part of that. You can. In this case, the nitrogens are just double bonded to each other. But those double bonds still make up a they still make up part of the aromatic system. For the last one, I disagree with the N rings being aromatic, but I definitely agree with the benzene rings being aromatic, because that should actually make them anti-aromatic based on the number of electrons, because that's 2, 4, 8. So that's just a mistake in the key. But otherwise, I agree that the benzene ring is aromatic. So yeah, I think that's just typo in the key. Those aren't supposed to be aromatic. I think the intent was to have a pyridine ring, and then the nitro just got thrown there to try to make it more complicated. Correct. You only count lone pairs if you need them. So a case of this would be tetrahydrofuran. So tetrahydrofuran, we have oxygen. This is an aromatic compound. We need the lone pairs on the oxygen to get it involved. But in something like pyridine, the nitrogen is already involved in the conjugated system because of the double bond, so we don't need to invoke its lone pairs. I mean, in principle, you could create a nitrogen analog of benzene. Like, there's nothing forbidding this from existing other than like just sheer stability. But this would be considered aromatic. You have a conjugated pi system. You have 4n plus 2 electrons. In this case, you need any of the lone pairs on the nitrogens. So for non-aromatic, can there be no rings or have rings and still not form anti-aromatic aromatic? Yes. You'll see lots of examples of that. So if you don't have a ring, you're automatically not aromatic. And so any like alkene would be, particularly any linear alkene, is going to be considered non-aromatic. They're kind of considered like obvious cases, but and then having rings and still not forming antiaromatic or aromatic, yeah, 1-cyclohexene, or just cyclohexene, or 1,3-cyclohexadiene. These are all situations where you have a ring and they're not aromatic by sheer merit of the fact that they just simply aren't conjugated. And that's why I gave you that checklist to go through, particularly with the discussion board, is like, is it a ring? If it's not a ring, it's automatically not aromatic. Are they conjugated? Okay, even though it's a ring, and if they're not conjugated, it's automatically not aromatic. And it's like, okay, now does it meet the 4n+2 rules? Like, okay, now you've got sufficient electrons to make the system aromatic. Yeah, you could still hypothetically create a I mean, this is a hypothetical molecule, but it 100% is aromatic because you have the conjugated pi system. This is just a benzene ring if you pulled off all the double bonds and broke them into anions and cations. A chalcone. So alpha beta unsaturated ketones you can definitely do if you're, well, it depends what you're making it from. And another option, and again, this would be kind of an esoteric example. In this case, boron has vacant p orbitals. So it's going to act like a carbocation. This, in principle, could be considered an aromatic system. You can get away without having pi bonds and making systems aromatic. They tend to be, these are more kind of very esoteric examples that don't exist in the real world. But they meet all our conditions. But the pi bond is just a way of supplying orbitals with the right shape to get this kind of conjugation. As for chalcone, you can do this by aldol condensation. So sodium hydroxide will extract the hydrogen. This will give you the anion, which will attack your benzaldehyde. Oops, missing a carbon in there. Hey, you're welcome. And then if you look at aldol condensation mechanisms, this will naturally deprotonate under acidic or basic conditions, or dehydrate under acidic or basic conditions to give you that compound. So this is all this is an aldol addition condensation mechanism. They're all going to look the same. All right, that's it for my office hours. Again, if you have any questions, please feel free to email reach out in advance. And I will see y'all, some of y'all tomorrow, and for the next live stream, I'll see y'all Thursday.